All right, what we're going to look at today is applications of antiderivatives or integrals. All right, so the first thing we need to talk about is some physics, because that's one of the applications. A while ago, when we first started doing derivatives, we looked at something, I called it S of t, which was a position function. This is like for projectiles when we had a position and we looked at like a velocity at a certain time. So we had a velocity function. And then we had the acceleration function. And like you guys use 10 meters per second squared in physics, I believe. I always call it 9.8 meters per second squared or 32 feet per second squared for your acceleration due to gravity. What we did before is we had this function, the original position function, which was a quadratic like this, and then we took the first derivative and we got a velocity at a certain time, which was linear, and then we took the second derivative and we got acceleration due to gravity, which was either 9.8 or 32, depending on which unit of measure you were in. Well, now that we can do antiderivatives and indefinite integrals, I can actually start with acceleration. If I know some acceleration, I can find the velocity, and then I could find the standard position function if I wanted. And I would do that by doing the opposite of taking the derivative. If I have the acceleration, if I take the antiderivative or the indefinite integral of the acceleration, I would get the velocity function. And if I know the velocity function, I can get the original position function. And so it's very useful. Like let's use negative 32 feet per second squared for our acceleration, because that's one we've used before. So if I want to know the velocity, let's say, of some ball, if I know that my acceleration due to gravity is negative 32 feet per second, I want to know the velocity of a ball that I threw. And I know that the velocity at time 0 is 50 feet per second. So basically that's the initial velocity, right? At time 0, that would be the initial velocity. I'm just using 0 to get easy numbers. So what I could do, if I want the velocity function, because sometimes I like to know the velocity function. So if I want the velocity function, I would have to integrate the acceleration. And I'm going to use dt here because we're talking about in terms of time. So if I integrate that, hopefully we've done enough of these that you realize that's negative 32t plus c. That's what the velocity equals. That's the general function for velocity, or general solution. I know at time 0, so when the time is 0, velocity equals 50, so 50 equals negative 32 times 0 plus c, so c is 50. So now I have a velocity function. The velocity function itself is negative 32t plus 50. So if I wanted to know the velocity when time was 6, I could plug 6 in here. If I wanted to know the velocity when time was 12, I would plug 12 in there. Okay? So what about if I wanted a position function? So let's say I actually want to get the position function. What would I have to do to get the position function? Well, I'd have to integrate again. So if I integrate negative 32t, I get negative 32t squared, because remember I add 1, and then I have to divide by 2, that's the power rule, plus 50t plus c. This is the general solution for the position. Well, let's pretend that I say s of 0 equals 10 feet. I'm just making something up. So let's pretend that my initial height, because it's time 0, was 10. So that would mean that this function, if I plug 0 in here and put 10 here, I'm going to get 10. So my position function is negative, I'm going to change that. How about we just make that negative 16 instead of 32 over 2. Negative 16t squared plus 50t plus 10. Now I use 0 for all of these. They might give you 1 or 3. It's the same thing. You just have to do algebra to find c. So this is my position function. So my next question, I have a velocity function, I have an acceleration function way up here somewhere, right? Yep, and then I have a position function. So now let's see if we can just answer some questions. How high does the ball go? How high does the ball go? That's my question. Well, that happens at a max. And in calculus, to find a max, we have to use what I would call the first derivative, right? So maxes happen at the first derivative. Which function would we consider the first derivative? Or better yet, a max happens when the velocity is 0, right? Because it goes up, then it goes down, and right at this point, the velocity is 0. So I have to use my velocity function, which was negative 32t plus 50, and I want to know when that equals 0. So if I solve that, I get, what would that be, 25 over 16. I don't know what that is right now, but we'll just pretend I do. Then that doesn't really tell me how high the ball goes. How do I actually know the height of the ball? To know the height of the ball, I'd have to use this position function because position is a height. So I would say, well, s of t equals negative 16. My time is 25 over 16 squared plus 50 times 25 over 16 plus 10, and that will give me my height. And the height is 49.0625 feet. That's how high the ball will go. How about the question, when does the ball hit the ground? So which function are you going to use there? When does the ball hit the ground? Well, ground would be, that's talking about height or position. So I'm going to use my position function, which is negative 16t squared plus 50t plus 10. And I want to know when it hits the ground. So basically I want to know when this equals 0. So I'm going to have to solve that. I'm going to divide by 2 first, so I get negative 8t squared plus 25t plus 5, and I'm not sure if that factors, so I'm just going to go ahead and use the quadratic formula. 25 squared minus 4 times negative 8 times 5, all divided by negative 16. And when I do, I get two answers. I get negative 0.1886 or 3.3134, I guess if you round it. Obviously, time's not negative, so this would be the time that it takes, 3.3 seconds for the ball to hit the ground. Okay, so what you're going to be doing with application problems, whether it's a ball or some types of acceleration that we'll talk about in class, is you're going to have to use antiderivatives to first come up with the functions. So that's what we did first. You're going to come up with the functions, and then you're going to answer questions, and you'll have to use either your velocity function or your position function that you find given of an acceleration. So basically they're going to give you acceleration, and you can find velocity and position and then use those answers to get some actual times and positions. All right, see you in class.